To go into some detail, let's take a look at how one might do locality-sensitive hashing for fingerprint matching. This example is covered in Rajaraman and Ullman, so you can read about it there as well. Fingerprints match if they're minutiae match. Now, minutiae is a technical term in the world of fingerprints, which I don't claim to understand in great detail, but things like islands, ridges, bifurcations, cores, crossovers, these are the terms used in that field. We won't get into the details of the different types of minutiae. Instead, we'll only worry about whether a particular print has some minutiae in a particular grid point. So we assume a grid of cells to be placed on the fingerprint, and we're only measuring whether or not a cell contains a minutiae of some kind. Now we define a function f of x for a print x, which is 1 if the print has minutiae in a specified set of k grid positions. So the function f depends on these particular k positions. We will use k equal to 3 in the example going forward. Notice that the function f is dependent on the choice of the k grid positions. If you choose a different set of grid positions, you'll get a different function f. Now let's consider the probability that any print has a minutiae in a particular position. Let that be p. Not every print has minutiae in every position, but across all possible prints, a particular position has minutiae with probability p. Let's assume that that distribution is uniform and the probability is p. Not necessarily a great assumption, but for our example, it will suffice. Now, the probability that f of x is equal to 1, that is that the print x has minutiae in all k positions, is p raised to the power k. So if you take the probability that a particular cell has minutiae is 0.2, the probability that a set of 3 chosen cells all have minutiae is obviously 0.2 raised to the power 3, which is 0.008. Now let's consider another print y, but from the same person. It's quite likely that this print will have minutiae in the same positions as x, but it's not always the case. So let's assign a probability q, which will be quite high, that the print y will have minutiae if x also does in a particular grid cell. Now let's look at the function f. What is the probability that f of x is 1 and f of y is also 1? Well, first of all, the probability that f of x is 1 is p to the k, so that needs to happen. But then you have the probability that y also has to have minutiae in the same k positions, so you multiply by q k times, so you get p q to the k. If q is 0.9, that means there's a 90% chance that y will have minutiae if x also does in a particular cell, then pq to the 3 works out to 0.006. Now that's not so nice that both x and y get a yes match with the function f is only happening with the probability 0.006.